Okay, so let's have a look over here. Calculate the forces required to make the seesaw balance. So first, let's have a look. How do they balance? We gotta see. Okay, how many? First, we gotta find where the pivot point is. That's the most important, right? Without the pivot point, there's no talking about torque. And then we can have a look, and we're gonna find which one is clockwise and which one is anti-clockwise. So this one have a torque. What direction is this? That's anti-clockwise, okay. And then this one is gonna be clockwise, right? Okay. How big is anti-clockwise torque? 2 times 1 become 2 Newton meter. So this one need to equal to 2 Newton meter, right? Yeah. So how much will be the force over here? 1 Newton. Yeah, that's it. So 1 Newton. Okay. Then we go the same thing for question 2. Again, this is exactly the same situation as this one. So this is going to be anti-clockwise torque, and this is going to be clockwise torque, right? Okay, and let's have a look. How big is the anti-clockwise torque this time?
4.
Yeah, this is pivot point. So this is 4 Newton meter. Yeah, don't write this down. Have a look over here. Sherry, sorry. Have a look. Okay, so now this is 4, so this one must be 4 as well. They need to balance, okay? 4 Newton meter. If it's 1 meter, how big is the force? 4 Newton, okay. All right, now this one is a little bit tricky. That's because this one, the pivot point, is actually over here. Now, which torque is going to be this one? Yeah, that is still anti-clockwise because it's making it going that way, right? And what about this one? That's your clockwise torque. Okay, so anti-clockwise torque. Okay, so force times distance. So how big is the force? 2 Newton, that's easy. What about the distance?
2.
Yeah, the distance is 2 because distance we specify is from the force to the pivot point. So this one is actually 2 times 2 equal to 4 Newton meter. Right? Okay, if that is 4 Newton meter, this one needs to be balanced, so this needs to equal to 4 Newton meter. So how big is the force over here? 4, right? And that 4 Newton times this 1 Newton will equal to 4 over there. Does it make sense? Okay, yeah. Don't write it down. Later have another try because we got the video here, so you can. Yeah, don't worry about it. Just first let's understand it, okay? And later have another thing. Oh, can I solve this question myself using the ideas we have? Okay. All right. Say over here. Same ideas as before, but now we have 1, 2, 3 force, right? Well, we're just gonna use the same idea. Well, let's say this is a pivot point. We're gonna find the direction of the torque. This one, what direction is this? Yeah, that's clockwise. This one, anti-clockwise. This one, also anti-clockwise. So now these two torque is gonna work together against this one over here. Does that make sense? Okay, so let's find out how much is this clockwise one. So yeah, so that's 3 Newton meter, right? Okay, and then how big is this one? 1. So how big does this one need to be? Need to be 2. The torque need to be 2 Newton meter. And then let's find out the distance. The distance from here to the pivot point is 2 meter. So how big does my force need to be?
0.5.
1.
Wait.
It's 1 times 2 equal to 2. The distance is 2 meter. Or I can go this. That torque equals to force times distance, and the distance is 2 meter. So I divide that 2 by this 2, so that's 1 Newton.
But then 1 plus 1 is 2, and then there's another 2, and then it equals 4. Because if you do the force times the distance.
Doesn't have to equal 3.
Yeah.
Yeah, but this one only times 1 meter. Because this one's distance is 1 meter. So 1 times 1 is 1 torque over here. And this is 1 times 2, which is 2. And add together equals to 3.
Oh, so you add them together, you don't do like the whole.
Oh, no, you don't times them together. The 2 torque add together to equal to that one, yeah. Okay, so let's have a look at this one. This one is the most confusing. Okay, Jasmine, can you have a look over here? Okay, so again, this is a pivot point. Okay, we're going to find which one is clockwise, which one is anti-clockwise. This one, what direction is this? Clockwise, right? Clockwise. This one? Anti-clockwise. What about this one? Yeah, that one is clockwise as well. So this one and this one actually gonna work together to cancel this one. Does it make sense? Okay, so let's have a look how big they are. This one, time distance 10. This one, 3. So how big does this one need to be? 7. Yeah, we know this one needs to be 7 Newton meter. And then the distance is 2. So how big is the force? 3.5 Newton. Because that's 3.5 times the 2 meter, the distance is 2 meter, that equals to 7. 7 add this 3 can cancel this 10. Does that make sense? Okay, I'll leave it here. Later you guys can have a think. But let's have a look at our last question here. Calculate the forces acts on the pivot point in the previous question. I want to calculate the forces acting on the pivot point over here. So far what we use is we use the second criteria for equilibrium. Is when the torque is all balanced, right? Okay, and then over here we're going to use the first criteria, say when all the forces need to be balanced. Say here, so far we have 1 Newton going down, 2 Newton going down, we got 3 Newton going down. Is that going to be balanced? Without the pivot point, this thing will start to accelerate downwards, right? So how big does the force I need to give it at the pivot point to keep it stable? Yeah, I have to give it 3 Newton going upward. And this 3 Newton will cancel this one and cancel this one going downwards. Does it make sense? So now I'm using my first criteria for equilibrium. Right? Okay, and then let's come to this one. How many forces are going downwards? 2 Newton going down, 4 Newton force going down. So how many force do I need to give it at pivot point to support it? 6. Yeah, so I need to give it 6 Newton. Okay, over here, a little bit different. Now, I got 2 Newton going down and 4 Newton going up. So what happened to the pivot point over here? Yeah, this pivot point, I actually need to 2 Newton hold it downwards to make it balance. Does this make sense? Yeah. Okay, coming to over here, same thing. 3 Newton going down, 1 Newton going down, 1 Newton going down, so I need 5 Newton going up. Yeah. So over here, 10 going down, 3 going down, so 13 going down, 10, 3. I don't look at torque anymore, right? I have to look at force. 13 going down, 3.5 going up, then I need another 9.5 going upwards. So now, all of these are going to be balanced at equilibrium. Does it make sense? Yeah, okay, see. So, okay, and then there is one last question. So I'm going to quickly talk about it and then give you guys some time to have a think about this one, okay? Okay, don't worry about writing down the answers because the key thing is you got to understand. So later you can have another look of that question and see if you can still do it, okay? All right, so this question is this. Question 3. Yeah, write this question down in your notes. This is a practical kind of situation question. I use a green pen to label the important things here. Okay, so we don't have too much time left. Can I, maybe you guys can take a picture at the end. So let me just quickly explain it first. Okay, all right, so let's all have a look. Yes, stop copying, let's all have a look. So for this question, I mean, like all talk question, the most important thing is the first you gotta find the pivot point. Yeah, because without a pivot point, there's no talk, right? Okay, gotta find the pivot point. And pivot point is where it's supporting, and this point is going to be the pivot point over here. Right? And then you can go calculate. Okay, question A is an achieve question, pretty easy. Torque equals to force and times distance. And put force there, 45 Newton, and distance, what do I use? 0.24, yes. Because it has to be meter, right? It's Newton meter, okay. So quickly put this in the calculator. So that will be able to give me a 10.8 Newton meter. Does this make sense? Okay, sweet. So now question B. This one, I'm going to give it a direction. This one is trying to go clockwise, yeah? So this is clockwise. And for all torque questions, basically you know you're going to be using torque clockwise equals torque anti-clockwise. Right? Because you know it's going to be an equilibrium position. That is the position where, let's have a think. The nail is trying to hold it down. You can see the nail has a force holding the thing downwards. This force. And this force have a anti-clockwise torque, which will balance this one. And when this one becomes slightly bigger than this one, that's when it starts to move. Does it make sense? So you got this, like kind of like equilibrium situation, and then your force gets just a little bit bigger. The nail is going to come out. Okay. All right. So now we'll say, well, I know clockwise torque is going to equal to 10.8. Then what is the anti-clockwise? Anti-clockwise torque is the force from the nail, and then times the the distance of the nail, which is actually 0.03. Because this force has this distance over here. Does it make sense? The distance does not need to be in the same line. So from here, you get F nail will equal to 10.8 divided by 0.03, and that will give you the answer. it will be 360 Newton. And you can see, by applying a 45 Newton, you created 360 Newton to get the nails out. Does that make sense? Okay, so when you guys go home, have a try of the question, rotational equilibrium, question 1 and question 2. Only do question 1 and question 2.